In this video, we are going to discuss about single electron transfer mechanism. Simply, we say as SET mechanism. Already, we have discussed the reaction mechanism that involves electrophile and nucleophile. If you recall, the nucleophile, say carbanion or negatively charged species, adds to electrophile to give the product. These two electrons are used to make bond between carbon and electrophile. Basically, two electrons are added to electrophile. Similarly, if you go for nucleophile, which has lone pair of electron, in that case also, the lone pair of electron is used to make bond. Two electrons are given to electrophile. After that, we get plus charge here. Next one, let us go for alkene. In that case also, this pi bond attacks the electrophile to give this one. Here also, this pi bond is equal to 2 electrons. So in all these cases, 2 electrons are added to electrophile. Is there any possibility to add 1 electron? Yes, it is possible. We can add 1 electron to the electrophiles. At this point, I would like to discuss about the oxidation potential of metals. You might have come across the oxidation potential in electrochemical series. Generally, metals as such, they are not stable. If you go for metal in zero oxidation state, they are highly unstable. It tries to lose its electron and it tries to achieve the more stable oxidation state. Only a few metals exist as such in the nature. They are known as native metals like gold and silver. They exist as such. Now, if you go for alkali metals like lithium, sodium, potassium, they will not exist as such even for a few minutes. If you keep that open, immediately they will get converted into lithium hydroxide or sodium hydroxide, potassium hydroxide, like that. That means they lose 1 electron. So I use this term to be easy. So it is 1 electron, not 1 negatively charged species. It is not lone pair. It is 1 electron. The reason, when it loses 1 electron, it gets more stable electronic configuration. In the outermost shell of lithium, there will be 1 electron, 1s2, 2s1. By losing the 1 electron, it becomes more stable. That is the driving force behind this. Similarly, if you go for magnesium, this can lose 2 electron and it can become Mg2+. Again, the electrons are not given as negative charge. They are 2 electrons. You should not consider this electron as the minus charge, whatever we use in carbanion or alkoxide. So it is 1 electron, like that 2 electrons are given. Now I go for few more metals like zinc. This also can give 2 electrons and it can become zinc 2+. The electronic configuration of this 3d10 4s2. So it can lose these 2 electrons to become zinc 2 plus. Another one, titanium 3 plus. As such, you go for titanium metal. It will have 4 electrons in the outermost shell. But if you go for titanium 3 plus, it will have only 1 electron in the outermost shell. By losing that, it will become titanium 4 plus. So these are some of the most common metals which readily gives single electron. Now let us see the reactions of these metals and its application. Before going to that, I would like you to recall the electrophiles. I categorize the electrophiles as carbene, nitrogen and benzene. This is the first category. The second category, carbocation and H plus. So basically positively charged species. Third one, atom attached with more electronegative atom via single bond, double bond or triple bond. For example, I go for halide. Even I go for alcohol, acid, aldehyde, ketone, ester, goes like this. In this case, this is more electronegative, so we get del plus on this. This is more electronegative, so we get del plus. Similarly, del plus here, del plus. This is the second category. Third one, alpha beta unsaturated system. In this particular carbon is del plus. Similarly, when you go for electron withdrawing group, this and this, they are electrophilic. So this is how I categorize. So I categorize into 4 different types. Now, is it possible to add single electron to these electrophiles? These two are generally known as intermediates. We cannot generate intermediates in the presence of the metals whatever I have mentioned earlier. So because of that, we can skip these two categories. So the metals and the intermediates and the condition whatever we use to make them, they are not compatible. What about the remaining two categories? Yes, it is possible. We can add single electron to all this electrophile. Not only that, even we can add single electron to the last category of nucleophile. If it is strong nucleophile, we cannot add. This alkyne and aromatic ring, they are weak. So we can add single electron to them because the nucleophilicity of them is very less. And you cannot add to carbanion or alkoxide. But you can add electron to alkyne and aromatic ring. Now let us discuss one by one. First, I go for acid. In carboxylic acid, we have del plus on this carbonate carbon. Also, we have del plus on this because oxygen is more electronegative. Now what happens when I add lithium to this or sodium to this? Lithium gives 1 electron here. Remember, this minus you should not consider as carbanion. It is only one electron. One electron is donated to hydrogen. Then this goes over oxygen. What we get is, and this minus combines with lithium. What about this hydrogen? This hydrogen will get one electron. This will combine with one more H. They will combine to liberate hydrogen. When you add alkali metal to acid, this is the reaction. Basically, one electron is transferred to more electropositive hydrogen atom. We get carboxylate. Not only this, even if you go for alcohol and if you add lithium, the same reaction will take place. Lithium or sodium. What you get is liberation of hydrogen. Suppose if you add this to phenol, you will get phenoxide. The mechanism is same. What about other metals? Can I go for zinc or magnesium? No. They are somewhat less reactive towards this hydrogen. Alkali metals which are highly reactive, they will undergo such liberation of hydrogen from the compound which has acidic proton. The next functional group, it is alkyl halide. Okay, general, you can say it is X. Since halogen, it is more electronegative, we have del plus on this. When I add sodium, sodium gives one electron. That one electron will be on this. This minus charge falls over iodine. So this bond I have placed on iodine. It has given one electron. So now I have got CH2. It is not radical, it is one electron. Further, one more electron, I write like this, will be given by another equivalent of lithium. We get minus charge. Now 2 electrons has been donated, so that is equal to minus charge. This, as soon as this minus charge is formed, it is nucleophile. In the reaction mixture, we have unreacted alkyl halide also. Immediately this will attack, and what you get is the coupled product. So alkyl iodide, in the presence of sodium, we get the coupled product, that is called Woods coupling. So basically it involves transfer of single electron to electropositive atom. I go for ester. When I go for alkali metal, say sodium, the electrophilic position in this is this carbonyl carbon. So the electron, single electron, will be delivered on this carbon. When it is delivered, this bond migrates over oxygen. Further, one more electron can be delivered. Because of that, we may get this one. Now this minus charge, carbanion, it is nucleophile. It can take proton and we get hydrogen here. The next step, two oxygen atoms are on the same carbon. So it eliminates ethanol or sodium ethoxide. We get aldehyde. If you repeat the same steps, whatever you have done here, the product, whatever you get, will be like this. One more hydrogen will be added. Another electron will be delivered here. This bond will go over oxygen. One more electron will be delivered. We will get minus charge. That will take proton. We will get alcohol. So basically, I have reduced ester to alcohol. This cannot be achieved by sodium borohydride. We have to go for LAH. LAH is somewhat expensive. Sodium is cheap, but it is dangerous to use. In industry, they go for this particular method to reduce ester because it is cheap compared to LAH. So this particular method is known as Bowelt blank reduction. It involves single electron transfer. Here itself it is very clear, aldehyde can be reduced via single electron transfer mechanism. What about ketone? Can we reduce ketone with sodium? Yes, we can reduce. It can be converted to the corresponding alcohol. The mechanism is same. But this can be easily reduced by sodium borohydride. So the condition with sodium borohydride is somewhat easy. But this particular method is generally used for the preparation of pinacol.